7th grade, lesson 10.2 is making inferences from random samples. And in this section, we will look at using, now that we've learned how to find random samples to find the information, or at least get an idea for information, how do we organize it so we can make an inference or make an educated guess about the information we gathered? They're going to cover 3 ways you could do it. One is using a dot plot. We'll show you that. You've probably seen before, but we'll show you how you can use that to get an understanding for the material you have. It just kind of lays it out there for you so you can see it. We'll look at box plots. Sometimes you'll hear it as box and whisker plot. I'll show you that. That has a lot to do with medians, the middle number. Or you can use proportions. So this lesson is going to show you how to use these 3 different possibilities, 3 different tools to sort out the information that you get out of your sample. And we'll start by looking at dot plots. Dot plots are exactly what the name says. You use dots to organize the data. So once you've gathered your random sample of information, then you can lay out the information in a way that makes it make sense. So as an example, Rosie asked a random sample of students how many books they had in their backpacks. She recorded the data as a list: 2, 6, 1, 0, 4, 1, 4, 2, and 2. To make a dot plot for the books carried by the samples of the students, we're going to go ahead and organize the information first in least to greatest order. So we would take this set of data and go in least to greatest order, and then we will go ahead and put the dots there. I mean, if you skip to the first step, it would be okay. You could skip that first step if you felt like it, if you just put it where the numbers are at. So we have 0, let me use a different color, 0, 1, 2, 3, 4, 5, 6. Now they say, let's go ahead and do step 1 and put the numbers in least to greatest order. So 0 is the smallest, 1, 1, 2, 2, 2, 4, 4, and 6. Then you would come over to your number line here and put a dot above it for each of these. Now the reason I said if you skip step 1 it wouldn't hurt, you're going to get the same thing. I would just put a dot at 2 for the first one, then a dot at 6, then a dot at 1, then a dot at 0, another one at 4, another one at 1, another one at 4, and another one at 2, and another one at 2. And I would get 0, 2 1s, 3 2s, no 3s, 2 4s, and 1 6. You get the same thing. The reason this is a good idea to do as a step is you don't lose your place as you go back and forth. So that will help organize it, make sure you get it right. But as long as you find a way to kind of keep your place as you're marking them, then you can look at that. Once you see the data laying out on the chart, you can start looking at like where are the areas where there were more numbers of that sample. So how are the number of dots you plotted related to the number of data values? There's the same amount of dots, one for each data value is what they're asking for there. And then as we look at this, we can draw some conclusions. Most students have what in comparison to one book in their backpack? Most of them have at least one. There's only one who doesn't have any, but most of them have at least one. Most students have fewer than how many books in their backpack? Well, there's one that has 6, but most of them have fewer than 5. Right? The majority of them are 4 or less. So we'll say fewer than 5 books in their backpack. And most students have between how many books in their backpack? Anywhere between 1 and 6. Well, most of them actually are between 1 and 4. There's just these outliers out here. So between 1 and 4, I guess. Between 1 and 4 books. Now, that's the data she has. So she kind of has, okay, so now for everybody at the school, most people are carrying, this is kind of the thing that she's going to use. Now, is that very accurate? I don't know. It may be accurate. It may be not. she has only asked, it depends on how big her school is, she's only asked 1, 2, 3, 4, 5, 6, 7, 8, 9 kids, right? So maybe if she asks more people, she will get an even more accurate picture as to what's going on. So what could she do to improve the quality of her data? Maybe ask a few more people or several more people to grow that sample, and then she'll have more data in here. And if it's still looking like this, she can be even more confident that that's that's what it's going to be on average for each student. So dot plots, simply put dots for the data and then look at it visually. The other way you could look at some of the data that you've gathered is using a box plot, or sometimes you'll hear that as a box and whisker plot. I'll show you why. And in order to get that information, if we take this data that was collected, this is the number of pets owned by a random sample of students at Park Middle School is shown below. They did their sample randomly, and so they got this data. And they want us to use this data to make a box plot. So one kid had 9 pets. I wonder what kind. 2 pets, 0, 4, 6, 3, 3, 2, and 5. This time it is important that you do step 1 and get them ordered from least to greatest. To make a box plot, you do need your data set ordered from least to greatest. So we have 0. Then we would have, looks like 2 is the next one. There's another 2. Then 3 and 3. Are there any more 3s in there? Nope. Then 4. That 0 was already put in there. Then 5, 6, and finally the 9. So now they are in order least to greatest. And just a quick reminder, median of a number set is when you line them up from least to greatest, you find the number that is right in the middle. And if it happens to be that 2 numbers share the middle, then you just find what would be right in the middle of them. You can add them up and divide by 2, or it might be obvious. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So the middle number would be right here with 4 on one side, 4 on the other, making 8, and that finally making the 9. This is the median, and that number is 3. Then what we will do is we would look at the middle. So you think of this as a lower side of the median and the upper side of the median. And you're going to look at the median of the lower side first. Lower side median is going to be this 2. Well, actually, it's going to be, the lower side is going to be these 2 2s. So right in the middle of that, well, that would be 2. Oh, sorry, that's supposed to be lower quartile. They call that the lower quartile. Then up here, this upper set, we're going to find out where that quartile ends, and it's going to be the median of these numbers. Well, these 2 are right in the middle. I need the number that would fall right in between them. Well, that'd be 5.5 or 5.5. And that's the upper quartile. The largest value 9, the least value 0. And so that's the organization of your thoughts on that. You find the median, and then you find the median of this upper set and the median of this lower set. And here's how it will look on the number line. So let's number our number line. 0. Okay, I numbered it 0 through 10. And then I'm going to mark with a line the median. Then I'm going to mark with another straight up and down line the upper level median for the upper quartile. That's 5.5 right here between the 5 and 6. Then I'm going to do the same for the lower quartile section. This lower section, the median of that gave me the ending of the lower quartile. That was 2. I'm going to box those off. This represents the majority of the numbers hung out in that section, with the very middle of all those sets right there. So you've got the majority leaning in this area. The whisker part, when I mentioned that that some people call it a box and whisker plot, the whisker part is just this. You always extend out from the quartile to the largest data set, 9, or the largest data in the set, and the smallest number in the set, 0. And those are supposed to look like whiskers, I guess. I don't know. Box and whiskers. Here's what these are representing. You have the main amount of data is right here in this center part, with the upper quartile leaning more numbers this way, lower quartile leaning lower numbers this way. So this is the middle amount. So this is where your majority of your data is at. It kind of extends out this way, but these are your quartiles. So you have your upper quartile, your lower quartile, and the right in the middle amount. And then this is your outliers for the highest value and the lowest value, box and whisker plot. The visual you're supposed to see is that the majority are in here. So on a dot plot, you'd see more dots up in this area. We can compare that to a dot plot just so you can see the comparison. I'll do a dot plot next to it. Okay, here's that same set of data in a dot plot form. You can see our quartiles here show up here as a little more bunched together. So it's the bunched together part. And there's a few more on this end. It's heavy on this end. That's why this median is leaning this way more. So that's the comparison. You see that they kind of lay out the information in a similar fashion. A good measure for the most likely number of pets looks like there's about 2 or 3, somewhere between 2 and 3, I guess 3-ish. 50% or half of the students have between 0 and 3 pets. This is the lower half, right? And then the other half have between 3 and 9 pets. And almost every student at Parkview has at least one pet, right? There's only the one that doesn't have any. Almost all of them have at least one pet, at least per the sample. Sometimes the way to make an inference about the information that you've gathered is by just using a proportional relationship. If this number is defective out of this number total, then out of the whole amount, we can expect this amount to be damaged. So you can use a proportional relationship. This kind of walks you through how. They do show you the way, one way to do it, and then I'll show you also another way to handle that proportional relationship in the event that you don't really see what number times what gets you there. So I'll show you both ways. So here's an example of a good way you can use proportional relationships with the data. A shipment to a warehouse consists of 3,500 MP3 players. Now, are you somebody who would like to go through all 3,500 of those MP3 players and figure out which ones work and which ones don't? Not really, right? We don't want to open up 3,500 of them. The manager chooses a random sample of 50 of those. Maybe going through 50 instead of 3,500 is better, right? And as he goes through those 50, he realizes 3 are defective. So how many MP3 players in the whole shipment are likely to be defective? Well, if the ratio of 3 out of 50 were defective, so find out how many were defective out of the amount of his sample. If 3 out of 50 were defective, then if we were to compare that to the whole shipment of 3,500, we can figure out how many might be defective if 3 out of 50 are. So the way they do this here is they say, okay, this is now a proportional relationship. It says equal, right? And I can look at 50 and think, what times 50 equals 3,500? Now you might notice that 70 does, and they noticed that. So if I did 50 times 70 to get 3,500, then I will do the same to the numerator, 3 times 70 to equal x, and that would be 210. So 210 out of those 3,500 very well might be defective, okay? If you didn't notice what number multiplied by this gives me to that, remember we can just use the cross multiplication to figure it out. Let's say I didn't notice that. Then I would just say, all right, because remember, if this says it's equal, then I can prove it by this multiplying these two will equal multiplying these two. So I'm using that to my advantage. I'm going to do 50 times x, which is just going to be 50x for right now. And 3 times 3,500 is going to be 10,500. Now I have a one-step equation. X is being multiplied by 50. I want to isolate the variable x. He's being multiplied. The inverse of multiply is divide by 50. I will do that to both sides of the equation to keep it balanced. And I will end up with 210, which is what they had ended up with here. It was just another way to go about it. Now, obviously, the easier way is, can I notice what 50 times what would give me 3,500? If I can notice that, or what number here would be, what would I multiply it by to equal that? If I can notice that, that's the easier way, and just multiply the top and bottom by that. But if your brain doesn't see it right away, this was that alternate where you can say, okay, I'm just going to multiply my crosses. This times this is going to equal this times this, run my calculation, and then inverse operations to isolate my variable, and you can still make it to the answer. So I wanted you to see you can still make it to that answer if you don't notice this part right away. Okay, and I want to look at one more with you, just with the proportional relationship one, just to kind of iron that down a little bit. Says a manager samples the receipts of every fifth person who goes through the line. So that's random. So he's getting a random sample. That's good. Out of 50 people, 4 had mispriced items. The price was wrong on their receipt. If 600 people go through the store each day, how many people would you expect to have a mispriced item? Well, here's our ratio of how many were mispriced out of the people he asked. So let's use that ratio as a tool. 4 people out of 50 had a mispriced item. If that's the case, and 600 people went through, just most of them were asked, how many can we guess, if we sampled this and got this ratio, how many can we guess had mispriced items? Now, once we have that laid out, this is what we're trying to find out. We're making that inference about this many would have had mispriced items, or could have had mispriced items. We can ask ourselves, 50 times what number would give me 600? If you notice right away, then multiply the numerator times that as well to find out what that will be. If you don't notice right away, no worries, multiply your crosses. 4 times 600 equals 50 times x. Now it is a one-step equation. Well, let me take care of this first. 4 times 600 is 2,400. This is now a one-step equation. My variable is x. I want him isolated. I'm going to do the opposite of multiply by x and multiply by 50 and divide by 50 to both sides of my equation. That leaves me with x isolated, and I just need to do my division. 2,400 divided by 50. That's going to be a 4, and that's going to be a 2,468. So 48 people might have had mispriced items. 48-ish, right? It's not going to be an exact number, but it's going to get us an idea of how many people may have had mispriced items if 4 out of 50 had mispriced items, and if 600 people walked through. And by the way, it was 50 times 12 that got 600, so I would do 4 times 12 to get 48. Now, I honestly didn't notice that right away, and I wasn't going to take the time to kind of figure it out. I could have done this divided by that to find out, but I'm just real comfortable with doing those multiply the crosses, and it goes pretty quickly for me, so I just go that way when I don't see it obvious. So always different paths for finding things in math.